Let's quickly begin with what I have studied about 3D reconstructions of crime scene during my time at Cranfield University while I was doing my master's. And it was great to hear Dr. David Erickson just before me. He was my supervisor back then. So hello, if you're here. As we know that crime scene documentation is a very integral part of any forensic investigative phase. And currently in the countries like UK, India, or any other Asian or European country in that region, there are no accepted limits of accuracy for taking measurements. And when I say accuracy for taking measurements, it is very important under the ISO 17025 that it is mandatory for all forensic science practitioners in the UK, EU, and the US to address competency testing, which means that all the measuring devices need to be calibrated, or they should have known standards as well as defined limits of error as well as accuracy for them to be acceptable in the code. As we know that crime scene could be anywhere. It is a physical location. It could be just outside or something which is indoor or outdoor, troubled by the weather, or any other location where your evidence is of prime importance. And over here, it may include a person's body as it's present on the slide. It may have buildings, vehicles, environmental related objects. And all of this, when all of this is taking place as an investigator, when I walk in over there, what is important for me is to establish everything that I see as it is without adding my perspective to it. When I say that I don't have to add my perspective to it, it means that I have to give the entire scene in such a way that it is unbiased, capturing each and every nook and corner, so that even if we have to revisit the crime scene after it has been recorded, we are free to do that. And that's why newer technologies like 3D reconstructions using 3D laser scanners, or even photogrammetry for that reason, can come to our aid as forensic investigators. A little bit about the background. So we know that technology has progressed from film photography to digital photography. Everything was black today, black and white. Today it's color. And similarly, traditional methods of documentation, as far as India is concerned, today also we are following a very laid back aspect of documentation. They're in the form of handwritten notes, sketches, videos, and photographs. Now, photogrammetry has already been used in forensic science to document bite marks, or to match weapon to the wound. So things like that keep happening with the use of photogrammetry. Similarly, 3D laser scanning technology, we have adopted it from the mining and the surveying industry. This study, we are going to take both these technologies, photogrammetry and 3D laser scanning, compare the two of them, and see how well our 3D models are coping up, how the measurements are coping up. Can we establish a positive relationship between them, or are they spread across in a very haphazard manner, where manual measurements are far more accurate than 3D measurements? Is that so? So let's just consider this case study. The aim of this case study is to determine the accuracy of 3D imaging as well as the manual methods. If it is accurate, then can it be taken to the court? Can we carry the crime scene to the court? Currently, we know that there are no standard procedures for forensic laser scanning, and acceptance of this data, if we are able to produce accurate models that can represent the entire scene in a very fair and accurate manner, will that be useful by many jurisdictions in different countries? And for that,
will be a recorded webinar. It will be put up online for subsequent viewing.
Yes, and so in order to
process, I recommend that you rewatch the area where we talk about the way that the margin of error is calculated. I hope that will. I do see a question in here about how sensitive the 3D software, which is a great question. So the question here, if I understand it correctly, is when we're recreating. So if I go back into input H here. Of course, it's going to be.
Dave, do we have anything?
Yes, sorry, Malvika. I think we've got an issue. If everyone can mute out when they're not talking, I think we've got a couple of people talking. So if you want to carry on, I think we'll try and sort that in the background. Sorry.
Okay, no problem, no problem. So overall, we need to provide a systematic approach for crime scene reconstructions. So we as investigators need to be trained. That was my outcome of this study. Moving on, traditional photography, there are some drawbacks as far as the photography is concerned. The first part is that we are capturing a 3D environment on a 2D projection. That means that already one dimension is lost. Next, we come to a bias where if I am the forensic photographer and if I am taking pictures of the scene, I will take it from my perspective, isn't it? Or if I have heard about some witness which is who is telling us about what happened, I may try to capture things from her perspective or maybe the victim's perspective. With this, what I am doing is I am trying to capture only what is available to me on a superficial level. I'm not trying to go inside, and later on some perspective which I don't think is important today, that might be important a year later. And then when we are looking at photographs, we have no place to go back to. And in such cases, information that is insignificant now will become very, very valuable later on. And that's why 3D modeling is my go-to area. A simple example that I've taken from one of the papers from 2017 by RAM. This is an image of how a footwear mark has been captured. The one on the left is a simple photograph. The photograph is lacking a lot of details. It is lacking the pattern of the shoe. It is lacking depth. Whereas if a plaster casting method is used, wherein we are pouring in a liquid in order to capture the depth and then taking that piece out, this process is very, very fragile. It is invasive. So in that way, we are not only damaging the evidence in case the plaster cast is good or bad, that is an after story, but we are damaging the entire evidence. After that, after the plaster casting is done, we don't have anything else that we can resort to. Also, the transport of the plaster cast would be very fragile. And what if it rains? Or what if it snows? So things like this will also influence the way we capture our evidence. Similarly, on the right is a 3D scan, which is able to capture a lot more detail. It is a non-destructive and a non-invasive method, which also means that we have lots of opportunity to share it digitally. So if I am an expert sitting in India and I want an opinion from somebody who is an expert in the UK or the US, I can simply share this data online and we can get opinions from the best of the best all over the world. It is also time and labor efficient. So this was my scene. As we can see on the screen, I have set up 3 scenes, scene 1, 2, and 3. These are 3 mock scenes, 2 being indoor in a 10 by 10 setup. And the third one is a mass grave because we wanted different kinds of evidences. So the first one is a living room setup where we have a dummy body with a gunshot wound in the skull, a bullet, blood spatter, and a pistol in a living room setup. Coming to scene 2 where the chair is placed, it is a kidnapping scenario with tie knots on the legs. It has broken cutlery, very visible, and a kitchen platform basically with lots of cupboards. Scene 3 is a mass grave with trace evidence, which includes soil, water, or tool marks. This was originally dug at the university for archaeology and anthropology. In scene 1 and 2, what I did was I placed 30 centimeter exactly measuring rulers in scene 1 and 2 randomly. So these white rulers, as you can see over here, these are the ones that measure exactly 30 centimeters and they were placed randomly all over the scene. I used Canon PowerShot G9X for photogrammetry and Faro Scene Focus 3D terrestrial scanner for 3D laser scanning. Now, after I captured the entire scene, the process was to conduct 3D modeling. For photogrammetry, I used the Agisoft Metashape software, and Faro had an inbuilt scene software that made work easier. Data analysis, once my models were ready, I took 3 types of measurements. One was a manual measurement. So in my manual measurements, I used a 16 feet tape, wherein I measured things like the sofa, the length and the width of the body, and the walls and similar structures around it. So similarly, we had 25 measurements each from photogrammetry as well and laser scanning too. And once we had all these 3 types of measurements, we did a comparison to find out the level of accuracy and if we could find something new. So this is how the photogrammetry technique is. For those who don't know about photogrammetry, it is a process of capturing multiple overlapping images following in one direction. So for example, if I have to capture this room, I will go from left to right, overlapping one frame over the other and click multiple images. Similarly, I will follow a pattern and go in one direction. So in this case, scene 1, I had taken 312 images. Scene 2, 199 images, and scene 3 was 77 images, out of which a few were not aligned, which means 297 were aligned out of 312. So here there may be a possibility that I have missed some frames which were not taken in by the software. This could cause a void in your data while doing 3D modeling. This is how the images looked. So all of these images, when stitched together, this will give me my photogrammetry model. And Agisoft Metashape was used for this processing. This is how it looked. So first step was to align the photographs. So all 297 out of 312 images were aligned. A dense cloud was built around it. So slowly, the process builds layer upon layer. A mesh is built. Finally, the texture is given, which makes it more realistic and gives us better, well-defined corners and edges. And finally, the model looked something like this. So we came from this step to this step. The processing took somewhere around total 32 to 72 hours, including different scenes. So scene 1 was the maximum time that I took, and scene 3 was the least because of the number of images that were less to process. Also, the format was, the models were exported in .psx, psz, and obj formats. This was how my laser scanning setup looked like. So scene 1 on the left-hand side, Faro laser scanner was used. The range of the scene was 10 meters indoors and 20 meters outside for scene 3. The scan duration, every scan took 7 minutes 49 seconds. So in scene 1, I did a test scan first to see if my device was calibrated and was set to capture the other scenes properly, followed by 4 different scans in scene 1, kept at different positions. So this is position 2, 3, and 4. And scene 2 had 3 scans. The workflow looked like this. So after taking the scans, I had to import the scans into the software, Faro software. It took me about 2 to 5 minutes, post which the processing took somewhere around 35 to 50 minutes for all three, for each scene. After that, the scans were registered. That took about another 30 to 50 minutes, so equal times. And then I was given an opportunity to explore the 3D model within the same environment. So these are the results, the output of my models. The one on the left is a photogrammetry model. Now in the photogrammetry model, the resolution as compared to a laser scanning model is comparatively low, but it still works for basic documentation processes. It has a weird, unusual haziness, a white kind of an overlay, and the structure of the white walls around. So the white walls over here, they are not very well defined as compared to the laser scanning model, which means that I can measure the walls over here, but I can't certainly measure the walls properly in a photogrammetry model. Also, compared to the resolution, laser scanning is at a higher resolution. This is the other view. So in the photogrammetry model, let's take, for example, if I have to look behind the sofa over here. Now, if I have missed the frame, if I've missed taking a picture of that part, I cannot certainly do that. Wherein in case of a laser scanner, if my scanner is positioned at that part, if I have managed to keep my scanner in a position where it captures all of these corners, I will be able to look even behind the sofa. As you can see over here, this is the white ruler that I had placed initially from my scenes. Coming to the black bucket, photogrammetry has managed to capture the black bucket. Of course, the quality of the edges is not very, very clear, but at least we know that there is this object. Compared to a laser scanner, I have not been able to capture the black metallic bucket over here because of it being black and shiny. That is a reflective surface. So laser scanners do not capture reflective surfaces. And that's why the bucket over here is not visible. Similarly, I can see the bullet over here, wherein in this case, I'm not able to see it. This could be a reason that my laser scanner has not captured that aspect. Maybe the positioning of the laser scanner is wrong. And in case of photogrammetry, possibly it was expected that I should have taken the images of each object properly in order to get that into my model. So training is very much important. That was my end result. This is scene 2. Scene 2 photogrammetry on the left hand side. Again, it has a very hazy, weird distortion over here. Another thing to notice is that the surrounding walls were white. It was plain white with nothing on it. That means no frame, no drills, nothing, which meant that when I'm taking overlapping pictures and processing it into the software cannot identify which point to match with which point. And that's why most of the data over here will appear merged with each other. Even the refrigerator part over here. Yes. So this part, the ones where there are blue patches present, this is simply a void in capturing the data. So the frames that have not been captured or the ones that have not been aligned while processing, they will cause a void in your data like this for a photogrammetric model. As compared to a laser scanning model, if my laser scanner is not able to reach certain areas, for example, the part below the platform, kitchen platform over here, they will miss capturing those important details. Similarly, the line of sight, the capturing was done at my line of sight. Wherever I could see, I managed to capture that because I kept the laser scanner in that position. Had I been trained, I would know how to uplift and keep changing positions and which perspectives are important. So that is why another miss in the data. The white fridge on the photogrammetry is again white, which merges with the walls behind, and that's why it's even more hazier. But in the laser scanner, we have managed to capture both the overlays very clearly. The area above the fridge over here, where the laser scanner cannot go or where it cannot reach, that has not been captured. So things like even in the previous case, the scene 1, where the body was lying, if the body is lying, we're not able to capture hidden surfaces underneath. So in that case, we might have to, after our evidence and everything is collected, post-processing of the scene, we may be able to capture that data again. Similarly, in photogrammetry, the black shiny surface as well as the metallic part of the knife that has been captured properly. Also, the scale is very much easy to read. So it's readable and doable again. Compared to the laser scanner model, being black and reflective, it has missed those points. But another example of possibly doing this would be to use a freestyle laser scanner. And with the freestyle laser scanner, once you're trained to use freestyle as well as terrestrial scanners, both those scans can be merged together to form a better product of your 3D model. This is how the kitchen scenario looked from right front. Over here, again, the cupboards are not visible very clearly. In this case, the cupboards are very, very clear and it has a very photorealistic quality. This is scene 3. Left one being a photogrammetry model, it has captured the water inside the grave very well, which means that if my scene is affected by environmental damages or anything, it will still manage to capture it if it's water. Similarly, a laser scanner has not captured water because it's a reflective surface. The laser scanning model is comparatively more crisper, which means it has well-defined edges, and that makes it easier for me to take measurements. Also, the depth in both these models are very evidently visible, which is excellent when we have to identify or measure the grave in a length, breadth, and depth pattern. Also, being an outdoor scene, this is what photogrammetry managed to capture. So it has captured only the object, the places where the camera had taken the photograph, wherein laser scanner captured the surroundings as well. So if I have to take a measurement from this tree to this tree, that is possible. Many a times what happens is we define our crime scene and cordon it off, but there may be more evidence just outside your cordoned area. And in this case, I see that laser scanners would be a better thing to opt for, especially in an outdoor scenario. These white spots that you can see in the laser scanning picture, these are the locations where the scanner was kept, where the tripod was kept. And that's why those are again voids in capturing the 3D model. So as an investigator, I need to be very careful when I'm choosing which location the scanner should come. And if I have missed that part, how does my next scan capture that area so that this void can be filled? Also, both these models will have an overview that you can see from the top, but laser scanning will give you the opportunity to view the scene from an aerial view. This is how my data set looked like. So after I had my models ready, I took 3 scans, 3 measurements each from the laser scanning model, then got an average from that, from all 25 objects, did a manual measurements. Then from the photogrammetry models, I took 3 measurements each and did an average. After that, I intercompared each of the processes. Some of the models, some of the objects did not give me a measurement because maybe the object was not captured or it was not very clear with the borders. So 2 of them did not match with the laser scanning, and similarly 2 were not there in photogrammetry as well. So that's why 27 objects are over here, but overall we took 25. This is how my statistics look like. So I used Minitab 19 to do these comparisons. This is a comparison chart between 3D laser scanning measurements. So all the 3 measurements that I took from my laser scanning models, they have been compared scene-wise. Over here, you can see that there are clustered columns which show very negligible difference amongst each other. So if one measurement is 0.12, the other is 0.12.25, and the other is 0.13, which shows that there is a very insignificant difference between each other. We bypass this.
Malvika, sorry, we've got 2 minutes, yeah?
Yeah. After that, photogrammetric measurements were compared, which again had negligible differences, and most of the differences were insignificant. Similarly, an intercomparison showed that my p-value clustered or around 0 in scene 1 and 2 being indoors, and whereas in scene 3, I see that the comparison between laser scanning and manual measurements is all over. It's spread all over the chart, which means that my hypothesis for scene 1 and 2 regarding the accuracy is true in the case of scene 1 and 2. And the reason for scene 3 for being spread all over, the only reason that I think is because we lack data. There was inadequate data. We need to work more with data, and that's why we will be able, that's how we will be able to identify the accuracy in that case. Similarly, photogrammetry, same results, clustered over here at 0, clustered over here at 0. Some outliers are present, but that's because of the object clarity, as well as the, if it was a bigger object, it gave me an outlier over here. The differences again in scene 3 are spread everywhere. Again, inadequate data in both cases. Over here, this matrix plot illustrates that the direction, the measurement direction is moving in the same pattern. So over here, what's important is that the measurements that I took from 3D laser scanner, the manual measurements and the photogrammetry measurements, they're all moving in a linear fashion. Even if there are some deviations, like in case of scene 2 over here, the deviations are also in the same pattern. Summarizing my study, that scene 1 and 2 being indoor and being comparatively smaller, it gave me sufficient data to work around with. Still, we need to work more with the accuracy levels. We are still not close to the 6.35 mm levels that are accepted by the courts in the UK, US. So that's why we need to do more work on these data. The nature of the scenes, the lack of objects, just the soil, may be a reason that scene 3 did not work out really well. But of course, it's a good way to demonstrate the depth and the length and the width of the grave. Single colored wall, we could not see any distinguishable features, and that's why it just merged with each other. And a point to think over here is that were the manual measurements accurate? They're always approximate values. So the error could be on that aspect as well. And minimum 3 measurements are required in order to attempt any check on accuracy. So photogrammetry or laser scanner, 3 measurements minimum required, and the average is also good. With this, I am leaving the floor open for any questions that I may have for me.
Thank you very much, Malvika. So we do have a question that's just come in. There's one here that said that somebody missed the beginning. So just let everyone know these will be recorded so you can watch them back. But how many photos did you take in the kitchen scene and what software did you use to combine the photos?
So the kitchen scene, I had taken 199 photographs, and out of which I think 157 were aligned, which meant those blue boxes that were there, those were the areas where the frames were missed. And the software that I used was Agisoft Metashape 2019.1 version, I think.
Okay, and as far as the processing, is that done on your computer, or is that a cloud-based sort of process, to stitch all the photos into a mesh?
So for the photogrammetry, I used my own device. My device had the latest configurations, being an i7, and it's very high on RAM, which meant that I could do a lot of processing with heavy files. The processing was done on the PC, not a cloud-based platform, and it took a lot of time, which meant that my laptop crashed multiple times during the processing stage. And if I hadn't had the backup of that data, I would have lost everything that I had captured. So that's one thing to note for photogrammetry. Always have backups, and the processing is going to take time.
Okay, and then another question came in. Obviously, with photogrammetry, you're kind of capturing the scene, and then it's sometime later that you know if you've got it correct. Is there a danger then that you could capture and miss something very important, and then the scene is cleared, in essence?
Yes, that's right. Because even in photogrammetry, what I am doing is taking overlapping pictures from my perspectives. Over here, it is again user dependent. Whereas compared to a laser scanning method, it is less user dependent. Of course, training matters, where you place your tripod, where you what settings you use. But overall, when you're doing photogrammetry, it's more focused on how the investigator is taking images. For example, is the image clear? Is it blur? Or has the scene, has any frame missed? So that way I am relying again on the person who is doing the photography. Similar as compared to a manual process, where the photographer's perspective as well as errors are again defined, being a completely user dependent job to do.
Understood.